Swayam Prabha. Digital India. Educated India.
Okay, morning. So in this lecture, I'll be talking about continuous Markov process. So far, we looked at several problems where the process was a jump process or a discrete process. So the system state is characterized by a set of discrete variables. Even if the underlying variable is continuous, we used to discretize them and then make it into a discrete variable, and we attack the problem through chemical master equation, Markov chains, where the systems goes from one state to the other state in a jumpy fashion. Okay, so we looked at several examples involving chemical reaction kinetics, diffusion, and many other chemical processes as well. Okay, so now we are actually stepping into another domain, which we call this as a continuous Markov process, where the samples path or the system's variables are continuous variables. Okay, if I have to give an example, if you look at Brownian motion and you want to study position of a Brownian particle, this position is a spatial variable and it can take a continuous values. Okay, so then we say that a Brownian motion in true sense can be addressed through a continuous Markov process. Or for example, if you want to look at Brownian particle but its velocities, okay, its velocity is also a continuous variable, then we can think about them as a continuous Markov process. So what I want to do is again go back to the differential Chapman-Kolmogorov equation, where we had one equation combining both jump and continuous Markov process, and now we drop the jump process and take only the continuous process, and then take some examples and then look at their solutions. So that's the idea. So the differential So just to remind you, this Chapman-Kolmogorov equation is the one that we derived for Markov process, okay, where the system does not remember its past, only the current state determines where the next step is going to be. Okay, so that's a Markov property. Any Markov process should follow Chapman-Kolmogorov equation, and we had an integral form and then we have a differential form. Differential form is more useful because if you want to study the kinetical or dynamical evolution of the system, a solution of the differential Chapman-Kolmogorov equation will give you that. Okay, so I'll write the full equation and then we'll look at the one that we are interested in. So, this variable p of x comma t y comma t prime, what this means is, this is the probability, right, that the system is found at state y at time t prime. Condition to this, what is the probability that the system will be found at state z at time t. Okay. So, that is the information that this particular variable holds, and this equation tells you how dynamically this function is evolving. Okay. So, now we have couple of mechanisms here. The first set here, it actually encodes the jump process, where the system can jump from one to the other in a discrete fashion. Okay. Whereas these two terms correspond to a continuous process, where if you look at the change between the states over a small period of time, it is going to be in the neighborhood of the previous state itself. Whereas these ones, jump can be very away from the current state. Okay. So, this entire thing is jump process. Okay, where so the difference between the current state and the next state, that displacement can be much larger than an infinitesimal value of epsilon. Okay. Whereas in the case of continuous case, we have this kind of condition, that the change in the state between two time points is much smaller than some infinitesimal limit. So, we can treat them as a continuous process. Okay. So, our discussion earlier had assumed a is 0, b is 0, these are all characteristic functions. Okay. Once you have these terms dropped out, then we have only jump process, and here we talked about chemical master equation, chemical kinetics, diffusion control reaction, etc., etc. Okay. So, now we will keep this one 0, W is 0, there is no jump process, and everything is having only continuous process. There are some other cases where you may have both happening. Okay. So, you may have a set of variable describe the system having continuous variable as well as discrete variable, then this is a total equation you have to deal with. Okay. But now we will talk about only this. So, we do not have this entire term. Starting from differential Chapman-Kolmogorov equation, when we deal with only the discrete process, we gave a name called chemical master equation. Similarly, now when I talk about only the continuous Markov process, this deserves a special name, and we call this as a Fokker-Planck equation. Fokker-Planck equations are basically the differential Chapman-Kolmogorov equation applied to a continuous Markov process. Okay. Differential Chapman-Kolmogorov is general, it includes all the jump and continuous process. Markov process that deals only with the jump process, we call them as a chemical master equation, and the one that we deal with only continuous case, we call as a Fokker-Planck equation. Yeah. Yeah. So, for the derivation purpose, we put in differential, the integral, but otherwise it is actually mostly a summation. All discrete jump process will have a summation term. In the original derivation, we kept it as an integral part, but actually when we try to use it, we never had a jump process with the integral sign, it's always a sum sign. Okay. It's for the notation purpose to keep everything. Okay. So, this becomes chemical master equation for jump, and this becomes Fokker-Planck equation for continuous. And I am highlighting and emphasizing this because depending upon where you study about stochastic process, people use different terminology in different places. Okay. So, this is, I am trying to kind of give it in one umbrella, what is the general equation and what are the limiting cases. Okay. So, So now just to remind you, these are the characteristic functions defined as the following. Okay, so limit So, when we deal with the continuous Markov process, we have to define two characteristic functions, function A, function B. Function A is defined, if you look at the original derivation of Chapman-Kolmogorov equation, we defined A as x minus z here is actually a mean difference. So, when the system is at z at time t, in the next time interval t plus delta t, it goes to state x. So, x minus z is nothing but the displacement. Suppose if I consider x and z as position of a Brownian particle, for example, then this will tell me over a time duration delta t what is the displacement. Okay, and this integral basically gives you the mean of that. Okay, because this is the first moment of this. This is a probability distribution function. This is the first moment of it. Okay, we are basically saying what is the mean change or the mean displacement per unit time. Okay, more like a mean velocity. Okay, that's why we call this as a drift. In the case of a pure Brownian particle, we know that the mean is 0, so the function A will be 0 for pure Brownian particle. On the other hand, if the Brownian particle is subjected to some sort of an external force, gravitational force, or if the Brownian particle is bound to a harmonic spring, then it would have a non-zero drift. Then the A will be a non-zero value. Similarly, the characteristic function B is basically related to the second moment of the displacement. Okay, and this second moment of displacement per unit time, okay, it characterizes diffusive behavior. Okay, so for a pure Brownian diffusion or a pure Brownian particle, this function will be 0, this will be a constant value corresponding to the diffusivity, because this is mean square displacement per unit time, that is nothing but diffusion coefficient. Okay, so now when you want to apply these continuous Markov process for any to model any process, our starting point will be defining what is A and what is D. That's where we have to think about and say, if I am going to model a particular process as a continuous Markov process, what are my characteristic functions? Is there a drift? Is there a non-zero drift or not? And how that is dependent on time and how that depends on the current position. Okay. Similarly, when I am thinking about the second function B, what is the nature of diffusion? Is it a free diffusion, or whether this diffusion itself is a function of position and time? This is where our input comes as a modeler. This is where we have to make a decision. How do I, because your solution and your characteristic of the solution is going to be very much dependent on what choices you are going to make for A and B. Okay, so this is where our input comes in. Yes. All right. Okay. So this is the general framework. Yeah. Drift plus. So like I was saying that if you consider a Brownian particle attached to a harmonic spring, okay, so then it would have a drift term, or if you think about a Brownian particle in a gravitational field, okay, so there's an external force acting on this particle. So that's going to give you a drift, okay, and also on top of that diffusion also playing a role, okay. Suppose when you keep this is 0, what would happen? If this becomes 0, then what you end up is actually a simple deterministic process, okay. So we'll talk about that also. So we have different combinations to choose between A and B, okay. I will discuss some classical examples of choices, and then later on we can look at some general cases also. So far good, I mean you understand, right? So differential Chapman-Kolmogorov equation, general descriptor of a Markov process including continuous and jump process. You kick off the continuous process, you have only a jump process, we call that as a chemical master equation. We solve discrete or jump Markov process using chemical master equation, chemical kinetics, discretized diffusions, diffusion and reaction, CSTR, batch reactor, all that we saw. Now we are saying, okay, let's keep the jump process out, consider only the continuous process. Then we have a Fokker-Planck equation, which again comes from here, okay. Now we want to focus attention to the continuous Markov process, and there are different kinds of continuous Markov process depending upon how you are going to deal with these characteristic functions, okay. Yes, yes, in the continuous case, yes. The first process we are going to deal with is called the Wiener process. It's a scientist name, Norbert Wiener, and so here let's say there is a stochastic process W of t describing the system state here, okay. We have not said what that is, okay. We will see later on. This basically refers to Brownian motion, okay. So we have a stochastic process. What's the stochastic process, by the way? What do we mean by stochastic process? Probability distribution function, back to class 0, huh? With the time what's happening? Probability is changing with respect to time, function of a and time, okay. And so basically yeah, stochastic process is a mathematical function where the system state changing with respect to time, okay. So here we have a process W which can take different values based on some underlying probability as a function of time, okay. It has got both random variable and a time to denote the evolution of the process, the kinetic the dynamical evolution of the process. So here we choose, as I said, we have to make a choice about the characteristic function. So here we take A z comma t 0, that means the drift is 0, the particle is not going anywhere, there is no drift, the mean position is 0, okay, or the rate of change of the mean position is 0. Then we say that the second function, we consider this as some 1 unity, okay. So there is a constant diffusion term and there is a 0 drift term. So this is a choice we are making. So then the Fokker-Planck equation for this case, we would write as long as it's a continuous process, yes. So what I have done here is I have taken the Fokker-Planck equation, I have changed the variable into W. This capital W we use to characterize the stochastic process, but then at any time t it can take different values, realizations. That variable I use small w, okay, that small w is a realization of the stochastic variable. So we are asking, if I know an initial state at t naught the system is at w naught, what's the probability that it will be at w at time t and the rate of change of that, okay. The first term is 0, it's gone, and the second term is 1, so we have just 1 by 2 this, okay. So I mean this looks little bit lengthy, so what we will do is we will just say P is nothing but this P of okay. So subsequent to this I am going to just use only P to denote this conditional probability. So then we have basically dou P by dou T is equal to 1 by 2 dou square P by dou W square, right. So that's a governing equation. This is a governing equation for a continuous Markov process with the mean or the drift is 0 and a constant diffusion. Yeah, so if you want to have a confinement, then that has to be encoded here in terms of the drift being non-zero. So here it's a free particle. I mean, I have not really told you what this signifies. We will first deal this problem mathematically, okay. Then we will say where this can be applicable, what physical system this can be useful, okay. So let's do purely from a mathematical aspect that I have chosen two characteristic functions. This is my governing equations. Then I need to solve them. So I am going to give the detailed solution of this equation in my notes, but here I would just write the final solution. So the idea is we are going to do we are going to define a characteristic function similar to Fourier transform s comma t So to solve this equation, we are defining a characteristic equation very similar to a Fourier transform, where we change the variable w to another variable s, okay. So our approach would be you multiply this equation with e power iws and then integrate on left side, both side, left side and right hand side, and then you will basically transform the partial differential equation into a an ODE, okay. And then you can solve the ODE, do the inverse transform, and then you can get the expression for P, okay. So if you suppose if you apply this transformation, what you will see is you will get if you use this transformation apply here, you will convert this PDE into an ODE like this, okay, in terms of a function phi, okay. And then if you solve this phi, take the inverse transform, and what you will get So when you use an initial condition which is a delta function centered at w naught, okay, it's like a unit delta function at time t equal to 0, w is located at w naught. Okay, so basically if I plot, if this is w naught, you basically have a delta function at t equal to 0, or sorry, t equal to t naught. That's an initial condition. For this initial condition, right, when you solve these equations, you will basically show that the probability distribution function basically becomes a Gaussian, right, and you can see that the mean of w is the initial position w naught, okay, and then the variance is nothing but t minus t naught. Sorry? This must be just this, yeah. So if you look at this function at time t equal to 0, this will be a delta function. For t larger than t naught, you will see that this is basically a Gaussian function. It spreads like a diffusive process. So here time is increasing. Right? So what we are predicting here is that the Wiener process that we have, if I start with the delta like function at the origin, here the origin is w naught, as a function of time, the distribution basically becomes Gaussian and continue to spread continuously, with the mean position being the same as the original position, whereas the variance of the distribution scales with the time. Okay, so this is a nature of a diffusive process or a Brownian motion. So this Wiener process characterizes the position of a Brownian motion, Brownian particle, free Brownian particle, right? You may recall that when we dealt with Brownian particle motion, we used Langevin equation where we predicted the mean and standard deviation, or mean and variance. And in those, while we discussed those moments, first moment, 0th moment, and the second moment onwards, I was telling that the distribution is actually Gaussian, and how we know it's a Gaussian, it's from here. Okay, we already looked at this functional form in one of the previous classes. The actual derivation comes from Fokker-Planck equation and solving them by this. Yeah. No, it is not coming from error function. Like I said, you have converted, so through this Fourier transform, no, you will have actually, you will have to do an inverse Fourier transform like this. Yeah. You won't have error function because you will actually integrate from minus infinity to plus infinity. Okay, so you will actually get a Gaussian integral directly, because if you see the range of W, range of S is actually minus infinity to plus infinity. So then you'll actually get a Gaussian integral, and that's what you'll get here. Any other comments, questions? Okay. So if you choose T naught, W naught 0, then basically you would actually get the solution for a Brownian motion like I mentioned before, okay, where mean is 0 and the variance scales as proportion to time t. So here you can see that we have not really used diffusion coefficient d, but actually in a Brownian motion there is a diffusion coefficient. So what we should have done is, if you use b is equal to 2d, instead of keeping b is equal to 1, this directly becomes applicable to Brownian motion, because this will also become 2d dt, 2d t, okay. So this is the diffusion coefficient, okay. So here the Wiener process involves only taking a is 0, b as 1, okay. Now if you want to apply this to Brownian motion, right, so you have to basically multiply, you have to assume this b is equal to 2d, okay, or you can actually convert. So you see this random variable w here is a Gaussian process, okay, actually it's a unit normal random variable, right, where the variance is given by t. Now if you want to apply this to a Brownian motion, all you need to do is, the mean does not change between the two, only the variance has to be scaled by a factor of 2d, okay. So then you basically have the Brownian motion captured. So from here what I can also do is, we can think about how to generate a trajectory from this kind of a probability distribution function. So let's go back to the basics of writing hierarchical functions for a Markov process. The hierarchical function Pn Okay, let me say what I'm trying to do here. I'm going to the definition of Markov process, where I'm looking at what is the probability of getting a trajectory of positions as a function of time. Let's say you might have seen this kind of description where I have an n point distribution. I'm looking at a trajectory containing n number of points describing the state of the system at n time points. So the particle position is at x1 at time t1, x2 at t2, all the way up to xn and tn. Okay, this is called the joint distribution function. You're looking at not about the probability of finding the position at one place, but you're looking at a whole lot of positions. Okay, this basically tells you the probability of finding this trajectory. The trajectory is nothing but the collection of these points. The suffix n here means I'm talking about n number of points. Okay, now using the Markov property, we can write this joint distribution function by writing a hierarchical functions. That is, starting from the first point p1 at x1 t1, you look at the probability of going from x1 to x2, x2 to x3, x3 to x4. So basically you are able to write a recursive formula because we know the information about the transition probability or the conditional probability. If I know the system at this, I know where the system is going to be. Okay, so when we discussed about stochastic process, Markov process, we wrote this kind of functions. If it is not a Markov process, we won't be able to write like this. Okay, we will need an explicit function for this. Now the fact that in Markov process only the current state determines the future state, we are able to write in a recursive fashion where is the current state or the initial state. From here onwards we write a subsequent rates like this. Now what I am doing is I take this Markov process or Markov property and then writing it for a Wiener process where I am just changing some so here what I am doing is I am just writing the same formula. Instead of x I am using w because I am talking about Wiener process with the characteristic functions a and b chosen already. Okay, so from here what I am doing is I am actually writing little differently. You see I am changing the order because I know the initial position is w0 at t0 and I am going all the way up to w1 tn. Okay, I am asking what is the probability of finding this trajectory. This is nothing but a probability of finding a trajectory of n points. Okay, so that can be written as the initial position, the probability of finding the initial position times this transition probability. Okay, and this transition probability is nothing but square root of, so we already know this function here, right? So you can write between, so here we have written between t and t0. So here we need between ti and ti plus 1. So that's why you can see here t is replaced by ti plus 1, t0 is replaced by ti multiplied by this exponential, this is replaced by wi plus 1, this is as wi here. Okay, now suppose if you define the subsequent displacements as delta wi, okay, wi plus 1 minus wi is delta wi. Similarly the time step, if you consider that to be a constant time interval, then this equation can be written simply as this. So what we are saying here is the probability of finding a trajectory of a Brownian particle or a Wiener process is nothing but you basically keep adding delta w sample from a Gaussian distribution or a normal distribution function. Okay, so you choose a delta t, sample delta w from this distribution, and that is what going to give you the probability of finding the next point. Okay, so what we can do is we can generate trajectories based on this distribution. So let's say you start with initial position at 0. Okay, choose a small delta t and then using the delta t you can sample what's delta w is. Okay, delta w can be either positive or negative because it's a Gaussian random variable. Okay, so maybe you find your particle here. Then from here for the same delta t you call another random number, Gaussian random number, which will be a delta w for the next time step. That can also be plus or minus depending upon the variable. So you may happen here. So you actually say, you will see that basically the trajectory getting formed, and you can generate many trajectory as you want. Okay, and this trajectory is nothing but this probability of finding this function. Okay, so the Wiener process that we are talking about is the one that characterizes a free Brownian particle in 1 dimensions. Okay, so that's an important message to learn from here. Sorry, for each delta t, yes, yes. So this is for a free Brownian particles position. So this is the first time we are showing the Brownian particles position in full description. Okay, we are getting the entire distribution function itself from the Fokker-Planck equation. Okay, till now we have been looking at only the first the mean position and the mean square displacement through chemical mass equation or through Langevin equation. We looked at only statistical properties. Only using this Fokker-Planck formulation, we are able to actually get the full entire distribution function for the evolution of Brownian particle position. Okay, so this is the very basic or the first example of a continuous Markov process. Okay, from now on there are other complications we can do. We can change the characteristic functions a and b so as to model other process. Okay, for example, if you have a Brownian particle, like I said, if you are not interested in just the position, but you are interested in the Brownian particle's velocity. Okay, so then we have to look at, okay, what is the mean velocity, whether there is any diffusive characteristic to the velocity itself, etc., etc. Okay, so we will see those things in the subsequent classes. Yes, any questions or any comments so far? Yes, sorry. Yeah, so trajectory, so I use trajectory in a very general sense, not necessarily a positional trajectory. Okay, for example, even when I have let's say a chemical reaction going on, and then I'm looking at the number of molecules evolving with time, even that I would call it as a trajectory. Okay, so trajectory need not be only about position versus time. Okay, so we are trying to use it in a more general term. Okay, or in other words, a time evolution of the system is what I call as a trajectory. It can be position, it can be other variables also. Not necessarily. Not necessarily. Like I said, I can have same mean and I can have the same mean and standard deviation, but may have a different kinds of distribution functions. No, that's what I'm trying to say, because you're looking at the evolution of the system. Okay, that's what I call as a trajectory. That depends on the underlying distribution, whether it's a Gaussian or not a Gaussian. Okay, so, yeah. Again, like I said before, if you remember a long time back, when I talked about the discrete or jump Markov process, there are only few functions that can satisfy Markov property: the exponential, the binomial, what else we talked, Poisson distribution, right? So we had set of distribution function, only those are able to characterize the Markov process. When we come to continuous distribution, the same thing happens. It will be always a Gaussian functions of different kinds. Okay, only Gaussian functions and Cauchy functions are able to characterize Markov property. Okay, so that's also something I want to remark here. Okay, we'll stop here.